In this video, we want to talk about one final important fact when we're dealing with limits for functions that have multiple variables. And you probably saw this as you were looking at, example number 8 previously, but there was this glaring note. One of the things that we're often going to be tempted to do, it's going to be such an easy temptation, is to again go ahead, take my values of x, y, and z, and imagine just plugging them in for x, y, and z. And sometimes what you're going to end up getting, like you would get here, is you're going to end up getting something like 0 in a numerator and 0 in a denominator. Sometimes you might get an infinity over an infinity, and you might then feel the urge to use L'Hopital's rule. There's just one problem. As the note suggests, L'Hopital's rule does not apply for multivariate functions. So if you have a function with multiple variables, sorry, you can't use L'Hopital's rule. It's almost kind of easy to think about, at the very least, why it would be difficult, even if it was possible. Because remember, L'Hopital's rule would have said that you would have needed to take the derivative of the top and the bottom of the fraction and redo the limit on that new fraction that you would create. But if you were to start setting up your fraction here, right? Imagine you're going to set up a limit and you're going to have your big fraction. How do you take the derivative of the bottom? How does that work? Because the only derivative rules that we've ever learned deal with functions that have a single variable, right? We would say y prime is equal to 2x. But if I have a function that's w equals x squared plus y squared plus z squared, how do I take the derivative? Remember that sometimes we could take our derivative and represent it with the notation of dw over d something. But here, if you say dx, then you're pretending x is a variable, but y is also a variable, and z is also a variable. So I can't just say this is just going to be 2x, or I can't just say it's 2x, 2y, 2z. That doesn't work. This is a whole separate, complex, messy idea that we're going to talk about in the next section. But for now, what we just have to recognize is that L'Hopital's rule here doesn't work. If we could, though, turn this function back into a function of a single variable, well, then we could definitely go ahead and attempt to use L'Hopital's rule. Okay, let's go ahead and take a look at what's going to happen here and how I might be able to turn this into a function of L'Hopital's rule without trying to progress how I can turn this into a function of a single variable so I can use L'Hopital's rule, without trying to deal with moving along any different sorts of paths. Okay, here's what I'm going to do. I'm going to create, first off, some sort of a substitution. I'm going to say, let's make t be equal to x squared plus y squared plus z squared, okay? I'm going to do that. I'm just going to pretend that x squared plus y squared plus z squared is the same thing as a t. Okay, so there's going to be more that I'm going to write here, but for the moment I'm going to hold off. I'm going to fill in more stuff here in a second. But note what this is going to change my limit into. I'm going to say our limit becomes, and if all I was doing is making this change, then notice that the limit that I have would look like 1 minus cosine of t over t. Now, I've left a lot of space here because I still have to figure out what in the world is going to be happening with what the limit is, or what's happening with the limit down here. How do I transform x, y, z approaching 0, 0, 0 into something else? So let's try to think about that. Let's go back up here. I can kind of see how the limit's progressing and changing. But what's going to happen with my limit notation? All right, if x, y, and z are all approaching 0, 0, or all approaching 0, then what does that mean is going to be happening to t? So I'm going to write this. If it's the case that x, y, z is approaching 0, 0, 0, then it would have to be the case that t is going to be approaching something. So for example, if all of these values were, say, approaching 1, then it might be easy to see that the final result of t is going to be approaching something close to a value of 3, right? Here, though, I can get even more specific. while x, y, and z are approaching 0, that kind of means that the total result of their addition should also be getting close to 0. But because each of these values is squared, notice that on the way to 0, 0, 0, whether I'm using negative values for x, y, and z, or positive values, or a combination of those, the results here are always going to be positive because they're getting squared. So that means that t is never, ever, ever going to be able to be a negative number. And so I can say that while it's approaching 0, it's approaching 0 from the right. Now, once I have that, that means that our limit has been reduced down to a limit like this. And this limit is a limit of one variable. It's a Calc 1 limit, which means I can use L'Hopital's rule on it. So notice here, since I have the case that I'm going to be approaching 0 on top and 0 on bottom, I can use L'Hopital's rule. L'Hopital's rule says, feel free to take the derivative of the top and the bottom and re-put them in place. I think that would get me something like this. Oops, sorry, that should say sine of t. And of course, then if I do the limit of this, I have a nice continuous function with the sine of t, so I can just plug it directly in. And I end up with this limit is 0. Okay. So I know now that this overall limit has an answer of 0. So this is the way that I can still make use of L'Hopital's rule, but it requires that I do this sort of transforming process. If you were to go ahead and take a look here at part B, I'm going to leave this one as an example for you to try, but I will go ahead and give you the hint to try to do something similar to what we did before. Could you try to go ahead and see if you could answer something like part B using t equaling x squared plus y squared? Then try to see if you can play around with what you end up with to see if you can calculate the limit here overall. You should end up with a final answer. It's not going to be undefined, or it won't end up being a does not exist limit. You definitely will end up with a final answer, but you're going to have to do a little bit of finagling to try to make it work. And of course, keep in mind that the full solutions are posted up online that you can check to see if your work is correct.